This lesson is entitled Mathematics and Historiography. Lynn Arthur Steen titled his inaugural address when he became president of the Mathematical Association of America, Mathematics, the Science of Patterns. That's the best definition of mathematics that I know. That's broad. That's why mathematics is beautiful. Patterns can be patterns of numbers, patterns of geometric shapes, patterns of motion. That's why we use calculus. Patterns of symmetry, geometric or otherwise. Patterns of reasoning. Patterns of data that you collect, for which we use statistics, or other patterns. Here's an example. When Jesus was born, mathematicians from Babylon brought him gifts. They found their way to him by a pattern of measuring, in this case, measuring the positions of an astronomical event that they saw from the east. In Jesus' day, and for thousands of years before that, the astronomers were the mathematicians, and the mathematicians were the astronomers. When Egyptians in 2000 BC restored land boundaries using a knotted rope in the form of a triangle with sides 3, 4, and 5 to get the needed right angles, they were using patterns of measurement. When Babylonians calculated the square root of 2 to a couple of hexadecimal places, they too were using patterns of measuring. Egypt used base 10, Babylonia used base 16. When Pythagoras in 500 BC discovered that in any right triangle with sides A and B and hypotenuse C, the square on the hypotenuse has the same area as the sum of the areas of the squares on the two other sides, he found a pattern. Conversely, the Pythagoreans discovered that if the areas of squares on sides A, B, and C of a triangle have that relation, then the triangle is a right angle. How do we find patterns? Intuition, generalization, by which I mean induction, trial and error, who knows what. It's not a given that you'll be able to find patterns. It requires a lot of hard work. But mathematics is a lot more than discovering patterns. It's about proving the patterns that you find. For example, the number pattern that I used in my introduction: 1, 2, 4, 8, 16, leading to the successive sums 1, 3, 7, 15, 31, might lead you to conjecture that the sum of powers of 2 is always 1 less than the next power of 2. But that's not a proof. We need to use deduction. In this case, the technique is deceptively called mathematical induction. We'll demonstrate it in class. Even though it's deductive, its name misleads. For a second example of discovering patterns and then forming deductions, the librarian of the Greek library in Alexandria, Egypt, Euclid, in 300 BC, wrote 5 volumes in which he proved things about geometry and about numbers. In Book 1, Proposition 47 is the law of Pythagoras. In Book 1, Proposition 48 is the converse of the law. Why does it take 47 propositions to get to them? Because Euclid is reasoning deductively from as few axioms as possible. Those are the 2 tools that mathematicians use. That is, tools for the science of patterns: discovering patterns and proving that they are indeed patterns. What about the tools of historiography? That's the science of history. There are many, but I'm going to pick on 2: context and provenance. Context. If you look at the clay tablet called Plimpton 322 in your course files, you will see a table of numbers. In 2002, historian of Babylonia, Eleanor Robson, argued from its context that it was an answer key for a teacher to be able to assign problems to his students. Prior to her explanation, two mathematicians had other theories. In 1957, Otto Neugebauer argued that it was a table to show how to generate Pythagorean triples, that is, integer solutions to the law of Pythagoras. In 1980, R. Creighton Buck argued that it was a table used to calculate angles for astronomical calculations. Namely, it was an early approach to trigonometry. In the videos that we will watch, Buck's explanation is omitted, but you'll hear the other two. Careful, Robson is not arguing that the Babylonians could not generate Pythagorean triples. She is not arguing that such triples were not helpful in their astronomy. She is merely saying that this particular table was not used for that purpose in its context. And now about provenance. If you watch Antiques Roadshow on TV, you know that the difference between something worth $50 and something worth $50,000 is being able to prove that the item is genuine. Historians want to know two questions about provenance. Where did you get your information, and how reliable is it? Let's look at where you got your information. For example, on the internet, there is an archive at archive.org to find things that used to be on the web but aren't anymore. But anyone can upload something to the archive, so it isn't automatically a reliable source, except for the exact purpose for which the archive is created, to remember snapshots of the web. I have a pet peeve about mathematicians. They don't footnote where they got their problems that they assign. They should, according to the rules of academic integrity. I will always do that. You will always footnote any source other than your own work, even if it's a mathematical fact, not an historical fact. Consider the 2nd century mathematician Claudius Ptolemy. That's spelled Ptolemy. His map, it is often said, was used by Christopher Columbus to find the New World in 1492. What is often not said is that the most widely circulated version of Columbus's time was the version printed in 1482, which was updated with all of the information known in that century. So it's not Ptolemy's map, and a proper footnote would make that clear. Second, how reliable is your information? E.T. Bell's book, Men of Mathematics, is a juicy, entertaining read about the history of mathematics. But it is notoriously unreliable. It is filled with rumors repeated without proof. Don't use it as one of your sources for your paper without other verification. What about Wikipedia? For mathematics, I found it always to be reliable. For history, it's reliable unless there's a box that contests an entry with words like neutral point of view, not respected, or sources not attributed, or some other caution. When in doubt, there's a talk page on a tab in Wikipedia that you can tab to find out what people think about the topic, how reliable they think the entry is. If you were to do that for Plimpton 322, you will see that Robson clarifies her remarks there very clearly. An interesting special case of this historical care for provenance is what has sometimes come to be called Stigler's Law of Eponymy. Stephen Stigler is an historian of statistics. Stigler's law says that a discovery is almost never named after its discoverer. Pascal's triangle was known to the Chinese hundreds of years before Pascal. The law of Pythagoras, as I've just argued, was known to the Babylonians thousands of years before Pythagoras. The Chinese in 1400 AD and possibly earlier, but without record, beat Carl Friedrich Gauss in 1800 to what you will learn in linear algebra is called Gaussian elimination. We might want to call it Chinese elimination. At Wikipedia, there is a long, long list of examples of Stigler's law, many of them mathematical. Here's a mathematical example of Stigler's law that is not on that list. L'Hopital's rule. That's the rule for finding limits of quotients that give an indeterminate form when you try to calculate them. L'Hopital did write the rule down. It was in the first calculus textbook, which he was the author of. He included the rule in it, but he didn't discover it. If you want to add L'Hopital's rule to the Wikipedia entry on examples of Stigler's law, then I recommend that you set for yourself the job of finding out who it was indeed who created L'Hopital's rule in the first place. The real irony is that Stigler's law is in itself an example of Stigler's law, since it was first proposed by sociologist Robert Merton. So maybe it should be called Merton's law. Let me summarize this unit. Both mathematicians and historians want their results to be reliable. Notice how they achieve their goals in different ways.